So I'm going to discuss the general technique. Okay, maybe this is just a review on you. And while we're looking at the parts, and you will see yung dinidiscuss natin doon sa angle. Okay, so the first thing that we're going to discuss, at least for today, hindi kaya yung buong session na tapusin to, yung tinatawag nating absorption spectroscopy. Okay, so basically, this is just what? Yung light na na-absorb. Okay, so when we're talking about absorption, so this is how matter absorb the energy. Okay, so in the absorption, if you're going to look at, tandaan nyo po yung Jablonski diagram. I think this is one thing that you need to learn from this course, yung tinatawag natin Jablonski diagram. So when we have an absorption there, so energy is going to be absorbed by your sample. And in doing so, okay, there is an excitation of the electron in your sample. So the way that you're going to look at this, the light or the electromagnetic radiation, okay, is absorbed by the atoms, the ions, or molecules in the given sample. And since there's absorption, so there's a transition from a lower to a higher energy state. Okay, and this is, we could say, one application. If you're going to look at chapter 4 of your Engel, yung tinatawag nating Planck, that results from what? The black body radiation, the one that revolutionized the concept of light as being a particle. Okay, so if we're going to look at the amount of energy, okay, that's just equals to the difference between the energy in the excited state minus the energy in the ground state. Now, depending on the amount of the energy here, it can be electronic, vibration, rotation, and translation. Okay, but usually, if we're talking about UVBs, it's all what we call electronic transition. So usually doon sa electron. Okay, so UVBs, we could say, from the electromagnetic radiation natin, so this is what? More energetic than this one. Okay, so we look at, if you recall in our previous discussion, the power and the intensity. So power is just the energy of beam that reaches a given area per second, while intensity is the power per unit solid angle. And the power and the intensity, we could say, is related to the amplitude square. I think we discussed that somewhere. Now, I'm not sure if it's chapter 1 or chapter 2 of the Engel. Okay, so if we're going to look at what happened here, so we could say we have the light, okay, coming in and the light coming out. And you see the difference. I don't know if you could see it. May animation ba kayo nakikita?
Meron, sir. Meron
okay, good. Okay, so as you can see, the power or the light that comes to the sample is more than the light that goes out of the sample. So the difference between them, we could say that's the absorbance. And for the absorbance, we usually use yung walang kamatayang Beer's law. Okay, so most of the things that we discuss here are not new to you. Okay, so parang ang nangyayari nga natin dito is we just doing some sort of a review on the concept of this absorption, but we try to understand it more. I don't know how you learn it in your undergrad, so hopefully by doing it here, anything that's not clear to you during that time will be clearer. So based on this, what we call Beer's law, the absorbance or the light that is absorbed by the sample is dependent on the path length the concentration of the sample and yung tinatawag natin proportional constant or yung molar absorptivity. So usually, we always set this as what? Yung letter B. Ano usually yung unit na ginagamit natin dyan?
1 centimeter po.
1 centimeter. Why? Because yun yung common cubet. Right? But you can use longer than that. But what's the problem if you're going to use longer than 1 centimeter? You're going to need
More sample.
Yeah. Because if you know, some cubet, di ba minsan yung buo. Tapos minsan yung parang ganun. Tapos minsan, ewan ko kung merong, I think meron naman dyan, no? Yung letter Y. But if you're going to look at this on this side, nilalagay mo siya na 1 centimeter. Parang ito. So usually ang nangyayari, ito yung front na makikita mo. Pero yung ina-analyze mo ay yung side. And some of the cubet are what? Roasted doon sa dalawang side. Because you only need, if let's say top view, di ba? So pwedeng ito yung frosted. Tapos yan yung papasok yung light. Now, even though you say, oh, this is not 1 centimeter, but the way that you're going to look at it, kumbaga, kaharap mo yan, piniplit mo siya, tapos doon, papasok yung light. But you can have more than 1 centimeter. It's just typical that 1 centimeter is the length. Magkano yung cubet yan ngayon? You have any idea?
So, alam ko lang po, thousands eh.
Because I think the last time we ordered, lagi kasing binabasag ng mga estudyante ko yung cubet eh. I think 175, the quartz cubet. So $175, so that would be really 1,000, right? Kasi, no, yeah, 1,000 nga. Because 100 is 5,000. So usually we have that thing there. Okay. So every year I ordered 4, but every year mapasag. Parang this semester yung quartz. Pinush niya todo yung tilt, ano yun? So meron kang F&R tube. Yung tip, pinush niya. Boom! Tawa ng tawa yung mag-groupmate. But the thing is, you can have more than 1 centimeter. And we have an experiment here to look at what's the effect of the absorbance if the length is not 1 centimeter. But since we always do that thing, ang nangyayari na lang, if you do some sort of a calibration is ganito. And all you need to do is, you know this one, you get the absorbance, you get the molar absorptivity. And then you use that molar absorptivity and then get the absorbance, you can get the concentration. That's the classic experiment that they do. I don't know if you know it. Doon sa mga blood analysis, if they want to determine creatinine or kung anong metabolite sa ating katawan, they already developed a method there. And some company, they patent it, and that's what they use. Okay, so the way that they do is they have known the molar absorptivity. Okay, and all you need to do is get the absorbance, and you can get the what we call the right concentration right away. And if you're going to look at the amount of light that I've absorbed, it can be dependent on the frequency or the wavelength. So you know the relationship between the two, right? Higher frequency and a wavelength. Shorter?
Shorter, sir.
Because frequency is just this. So if the wavelength is shorter, there's high frequency. So frequency is the number of times in a given time, the number of frequency, yung distance na meron dyan. So if it's shorter, so mas madami yung what we call frequency, mas higher. And the good thing about this is the absorbance is directly proportional to the concentration of Fe2 plus. You can have your own private lab, even with just spectronic 20. Okay, because of this principle. So if we're going to look at the Beer's law, ano yung meron sa atin dyan? Digital na ba? Or analog pa rin?
Digital na po, sir.
Digital na? Okay.
Apo.
Because before the absorbance was what we call developed, usually transmittance the one that was developed. And if you're going to look at the transmittance, that's just the ratio, okay, of the light that comes out over the light that comes in. Okay, so you can look at the percent transmittance as just equals to what? 100T. Okay, so kapag same yung amount nito, so that is equals to what? Yung T. So kapag pareho yung dalawa, so ibig sabihin, let's say 1 over 1. So that's equals to 1 times 100. So you have 100% transmittance. And if you have 100% transmittance, that means nothing was absorbed. Okay? Now, in terms of the absorbance, what they do is they put it as a negative, nasanay ako sa pH. This equals to log, okay, over what we call the lights that comes in over the lights that comes out. And if you're going to what we call look at the relationship that they have, ito yung makikita mo. And if you have an old analog, usually that's how they have here. So all you need to do is tell where the line fell when you look at the absorbance. But I think what you have right now is already digital. So either you can get the absorbance or the transmittance right away. So if there's no light absorbs, there's 100% transmittance and the absorbance is 0. And if all light are absorbed, the transmittance is 0 and the absorbance is infinite. But what's the max absorbance that we want? Anyone?
1.
Okay, 1. As much as possible, you don't want it to be like this one. Maybe you are curious why. Bakit 1? Why do you set the absorbance as the max as equals to 1? Nah. Have you wondered why? What? Okay, sige, Jeff.
Dahil po sa limitation ng Beer's law na true lang siya at low concentrations. Pag masyadong concentrated na,
Okay.
hindi na siya nag-hold kasi may interactions na yung analyte.
Now, we could say, what does an absorbance of 2 means in percent transmittance? So, punta tayo doon sa ano, yung absorbance of 2. So that means, anong equivalent nito? 1% ng transmittance. So anong ibig sabihin pag 1% ng transmittance? Almost 99% ang available light na nabla-block or na-absorb ng sample. Okay? Now, kapag, let's say, yung absorbance mo ay 3, ano yung percentage transmittance mo? Remember, what's the relationship between the two? Anong relationship ng transmittance sa absorbance? If you're going to look at this, usually this one, right? Log. So if you have an absorbance that is equals to 3, so that means only 0.1% is transmitted. So the amount of the of the light that is black is so high. So we could say this ranges is outside the meaningful range of most the spectrometer that we do. So what do we do? If your reading is more than 1, ano ginagawa mo kapag yung reading absorbance mo more than 1?
Or nag-a-apply po ng dilution.
Okay, you have to dilute. Okay. There are some instruments that they can go over that one. It's more expensive, but the idea that you do is you have to what we call set the absorbance maximum as equals to 1. Ang main explanation nga, because at 1, you could say that, oh, at least there's still 10% of light that is being transmitted. So kapag tumaas yan, magiging 1% na lang. Pag ginawa mo pang 3, magiging 0.1% na lang. So you lose a 10 for every absorbance. Okay? Difference of 1, 2, and 3. Okay? So maybe, I don't know if you have learned what we call the main reason bakit we have to make it equals to 1. Because if you're going to look at this one, ito talaga yung ano nila. Absorbance is negative log of the percent transmittance over 100. And as I have told you, molar absorptivity, we could say, is a property that can be used to identify or quantify a certain compound. But for you to get the molar absorptivity, you have to do some standardization first. And when you do this standardization, you always have set a limit like this one. Okay. So if you measure the absorbance or percent transmittance at a given frequency, you can get you information related to the amount of the sample present with an identified molar absorptivity and absorbance. And when you do, okay, the Beer's law, as much as possible, you don't want to have an absorbance that is larger than 1. Because there are some deviations that will happen. Okay. And sometimes there are some happening in terms of when we go to fluorescence, at higher concentration, there could be quenching. So the reading that you have there is not proportional already. So as much as possible, you go to the point that it is linear, but set the max as around 1.0. Okay. Now, maybe this is, we could say, you know this by heart. Yung tinatawag nating schematic diagram. Okay? I remember when I was a student, I think all of us, I don't know when you are a student undergrad, you're required to draw the schematic diagram of all the instrument that you have. So usually hindi pa ganyan, di ba? Yung mga box pa, tapos ganun. But we could say the number one that we have, if we have spectroscopy, is the so-called light source. Without any light source, I don't know if you're going to have a spectroscopy or spectrometry. Because that's where you get the energy, okay? And then you can have the entrance slit, and then you have the dispersion device. So ano usually yung dispersion device natin? Out of the dispersion device, dyan lalabas yung exit slit. But in reality, ano yung term na usually ginagamit natin dito? Na pinadami lang natin. That is your what? Ano yan yung ano dito?
Monochromator.
Okay? So yan yung monochromator mo. In some, they use filter. Because we all know that your sample will be, we could say, has the largest absorbance at a certain wavelength. And to bring you to that certain wavelength, you're going to have this monochromator. Look at the word, mono and then chromo, one color. And then you have the sample. And then you have what we call the detector. Now, sometimes dito, pwede ka pang mag-ano, di ba? May isa ka pang cuvette. Tapos ano nilalagay mo doon? Yung reference mo. Right? Ang tawag dyan? Double beam, single beam. Buhay pa ba yung double beam spectrometer natin?
Buhay pa po, sir.
Nagagamit pa?
Pang demo lang po ata, sir.
Pag single beam is always spectronic 20, double beam yun. Okay? So the way that you do, you have a light source, a wavelength selector, which can be a monochromator or filter, a sample holder, and then a detector. And then usually it's a detector. Detector usually, you don't understand it. So you will have either a detector or a recorder. So what the recorder do is transmit the signal from the detector to one that you can understand. So maybe a number, or if you have the analog, yung paikot-ikot. Okay. So this is, we could say, the basic design. And we can look at the desired properties of each of the components, especially the one that we use in UVPs. So iisa-isahin natin yan at least today. So we have what we call the light source. So the light source creates the proper wavelength. So one desired properties that we have is it should be stable. How do we make it stable? Anyone? Sa experience nyo, wala ang tubig. Ano usually yung ginagawa nyo? Whenever you use spectronic 20 or spectroscopic method, spectrometer, ano ginagawa nyo?
Sir, parang open muna siya for some time bago
Okay.
gamitin talaga.
Yep. You don't usually do that. Oh, I open and then i-read mo na agad. You warm it for some time. Okay? Because what you want is you want to have a constant power. And a constant power will give you a good precision. But if you do it, minsan nagmamadali. Hindi pa stable yung power niya by that time. Okay? Another thing that we have is it should be intense. Because remember, you are getting the light energy or the energy there. So you want it to be powerful. Okay? Later on, I'll show you the light source that we typically use here. And usually they have different power. But what do you think is the most powerful? Let's say the typical lamp that you know, compare it with what we call the laser. if your light source is a laser, you have to be very careful. It's so powerful. I think I destroyed one detector before because I didn't. It's my first time to use a laser. Sunog yung PDA. Nagtaka kami, ang taas ng signal, tapos biglang 0. And then it's just 0. So tinanong ng professor, what happened? Why did you get the new guy? Ako yung new guy. Do that. So it has to be intense. Okay? Para makita agad yung absorbance. I mean, when you apply it to the sample, okay, the sample will be able to absorb it right away. Now, the narrow band pass, or the next one is the monochromator, which is the wavelength selector. And usually, you want it to be a narrow band pass. Okay, you select the desired wavelength. In the monochromator, you can have a filter. You can have the monochromators, which can be what? The prisms, the gratings, and the slits. Napanood nyo ba yung mga video? Kung ano yung pwede maging wavelength selector. Okay? You can have the prisms, the gratings, or the slits. Or you can have what we call the filter. Okay? So what does it do? You want it to have a large light throughput so it can increase the power. Okay? Increasing the power would make the electronic transition better. And if you have a better electronic transition, you're going to get a better signal. Pag hindi powerful yung ano mo, light source, hindi, baka wala kang makuhang signal. Okay? So you want the light source that you have when it goes through a wavelength selector, you maintain the power. The only difference is it's at a certain wavelength. Okay? And then you have the sample cell holder. And it's usually fixed geometry. So dyan pumapasok yung cubet. A constant B. So you don't want to use different sizes. If you use 1 centimeter, you use 1 centimeter. We have a cubet here that is just around 0.5 centimeter. So what happened in the sample holder, that's where the absorption of your sample takes place. So it transmits the wavelength of interest. Okay. Now, as much as possible, you want it to have an increased power also. So dyan papasok yung difference ng quartz, glass, and the plastic. Right? Which one you can use at all wavelength? Alin dyan yung pwede mo gamitin sa lahat ng wavelength? Okay, you will know later on. So, saan gagamitin yung quartz, kailan gagamitin yung glass, at kailan gagamitin yung plastic. And then, the fourth one, we have what we call the detector. Okay? So usually, yung detector na yan yung tinatawag nating transducer. So you can be a phototube, it can be a photomultipliers, yung PMT, it can be a photodiode array. So usually, yung photodiode array, it's a multi-channel photon transducer. So you can have the charge transfer device, the charge injection devices, or the charge coupled devices. Okay. I think that's one of the question in your exam, right? Tama ba ako? Or baka sa ibang course yun binigay ko? Sa infrared, usually yung thermal transducers yung ginagamit dyan. But for now, we stick with this one. So again, you want it to be stable. You want it also to be sensitive to the wavelength of interest. Now, what we're going to do, we discuss each one of them. So we go first with the light source. So number one light source that we have is the deuterium and hydrogen lamp. So usually that's the one that you use at UV range. Okay. So if you're going to look at the light source that is deuterium, based on the slide that we have here, it is continuous source. So it is a continuous source that this is a broadband. It has a broad range of frequency. And if you're going to look at this, it is based on the electric excitation of your hydrogen or deuterium at low pressure. So it looks like that one. In the presence of the arc, some of the electrical energy is absorbed by deuterium or hydrogen, which results in the dissociation of the gas and the release of the light. So yan yung source ng light. Okay? So merong energy doon, electrical energy na iaano mo sa deuterium, so ma-excite siya, and in their excitement, okay, what happens is you produce a light, at yan yung nagiging light source mo sa deuterium. And if you're going to look at the light source, okay, it varies from, ito yung range niya, 160 to 375. Okay. Now you might say, why a difference in the wavelength? It is due to the different frequency in the excited deuterium. Now, if you're going to use here, your sample cells should what we call be quartz. Kasi yung glass, hindi siya nag-absorb lower than 350 nanometer. But I think you know it by now. Now, the cost of it is around $350 to $500 here. And if you're going to look at the intensity, so you could see here, yung ano niya is at around here. Higher than that, mababa na yung intensity niya. And usually, if it's a UV base, ito lang yung pang UV. Okay? But if it's a UV-based region that you do, either you have this and included another light source beyond 375, or you're going to use the tungsten lamp. So just like your deuterium is a continuous source, broadband in nature, and this is based on the black body radiation, like this one. So doon sa black body radiation, as they increase the temperature, they found out that there's a blue shift of the resulting spectra. Pero hindi siya continuous. Okay? It gives you at a certain what? Intensity. Kasi ina-expect nila doon, pag increase ng temperature, i-increase din continuously yung power na makikita nila, kaso hindi. Okay? So if you what we could read the introduction in the chapter 4 about the black body radiation, so usually yung black body yung nag-absorb lang siya ng energy. Okay? So if you're going to look at the black body, it absorbs all the radiant energy incident upon it, regardless of whatever's the wavelength. So hindi kayang i-explain ng classical physics during that time ng phenomenon. So as they say, if you cannot explain, you propose a new theory on why the behavior is like that. Okay? So you have here a heat solid filament to glowing light emitted will be characteristic of temperature more than the nature of the solid filament. Sa tungsten, ano ng tungsten? Chemical symbol. Anyone?
W, sir.
Ito daw yung lagi minimension ko pag lasing. Nung college. So Wolfram, the German name of tungsten. And if you're going to look at this, okay, the lambda max of this, we could say is inversely proportional to temperature. So typical tungsten lamp is around 208,000, 2,870 Kelvin. And the range that you have here is 350 to 250. So usually if you have a UV piece, it's a combination of the deuterium lamp and the tungsten lamp. I think it is there in our double beam. Because what happened there, I don't know if you use it, if you try to scan from the UV region going to the visible region, you will see that when the reading is going up or longer, you can say it's just like there's a switch in the light source. That's what I observed because I thought 137.1 before I left the UPLB before. Yeah, familiar ako dun sa experiment ng 137.1 during that time, and I think it might still be the same. So if you're going to look at the what we call the visible region is the one here. So covered pa siya, okay, nung portrait ng intensity versus wavelength for different temperature. So these are the one that commonly used sa old model. But now, okay, most of them use this one. But this is famously used not in UV base, maybe when we go to the fluorescent, that's the one where they use this thing. If you go on the recording that I have for the 137.1, I think the way I presented it there is all the light source of the different spectroscopic method. So dito iniisa-isa natin. That's why this is, we could say, from a different perspective. So just like the first two, they're always what we call continuous source. We don't see any line source, at least in UVBs. Okay. What do you think is the line source? Ano yung line source na light source na line in a particular line?
Cathode tube.
A cathode tube. But what else? Usually, dyan pumapasok yung laser. Laser has only what? A specific wavelength. I think in the Desamero group when I'm working, we have a 488 nanometer laser and a 532 laser. And then he bought another one. He make it at a lower wavelength. Okay. So the xenon arc lamp, this is the good thing. It can cover the UV region. Okay. Now, the way that it do, just like xenon, I mean, the passage of current through xenon causes thermal excitation, which is just a black body emission. It gives very intense radiation over a frequency range. It was developed for searchlights during the World War II. You know the searchlight, yung parang powerful na flashlight nila. There's only a problem here: higher heat, more stray light, higher cost, and this one, shorter lifetime. I remember when I was a grad student, nasira yung power supply namin. Luma na yung instrument. Hindi namin alam saan kami bibili ng power supply. The power supply that has the silicon cloud. So if you're going to look at the profiles that you have here, so ito lang yung nako-cover niya, around 250. So you can have here the UVBs until the one here. Okay. So yan yung light source, at least in the UVBs. Okay. We don't cover laser. You don't usually have laser in UVBs because laser is monochromatic. So you can only scan for one wavelength if it's a laser. And if it's a laser, I don't think you're going to need this one. Right? So the next thing that we have is the so-called monochromator. So if we have this, what we call monochromator, okay, this is where the separation takes place. So if you're going to look at this monochromator, it allows only certain wavelengths to be selected and used. So the way that the monochromators, you have the polychromatic light, so that's your broadband. Okay, so what the monochromator does is separate the frequency from the polychromatic, what we call light. And there are some, we could say, form of the monochromator. Okay, so you can have this dispersing monochromator, and the one that we have there is prism. Have you seen a real prism? Na-experience nyo ba makakita yung tunay na prism? When you pass the light, you will see the rainbow color.
Or parang sa physics lab po.
Sa physics lab, meron, wala sa chem.
Apo.
Because you only use it in optics.
Yes po.
During my grad school, I have, because I have three groups that I work with. So we have that thing doon sa my laser system. And we really, whenever we don't have anything to do, we're so bored because it's snowing outside sa Buffalo. So we just say, can we do something? So try namin yan. So nakita namin to. You pass any light source there and it will give you a rainbow color, yung prism. So if you have this, what we call prism, so there's a refraction of light, and the fact that there's a different wavelength that has different refraction index in the medium. So I told you, yung dinidiscuss natin sa Ingel, okay, ito yung parang overall application na. And you can look, since there's what we call a dispersing monochromator, you look at this so-called dispersion curve, where the chains, okay, of your refractive index is a function of wavelength. So normally you want to work in areas of normal dispersions for prisms. So you can have this anomalous dispersion that occurs where the substance absorbs light. So as much as possible, you want the one that refract. Okay. So if you're going to look at this dispersion curve, so you could see it here. So the near UV, the visible, and as you approach the near infrared wavelength, so you see the refractive index already go down a little bit. And maybe you're familiar with this, right? we have it in chapter 3, the Snell's law of refraction. So for the refractive index 1 times sine theta of that same sample equals to the second refractive index equals to sine theta 2. Okay, so if there are what we call equals to 0, the theta that you have there, the angle that you have there, okay, you don't have any refraction. So the way that you look at the light, I mean, how you could see refraction when you put the light on the prism, okay, it should be at a certain angle. And the way that they said they use is 60% angle. Now, this is the dispersing monochromator. We also have the so-called grating. So the dispersing is based on refraction. Yung grating naman, it's based on diffraction. So dyan pumapasok yung constructive and deconstructive interference. Deconstructive eh. You see the term that they have, this is just what? Doon sa book natin. This is just destructive. Now, even in this grating, we could say monochromator, you can still classify them as either what? Transmission grating or yung tinatawag nating reflection grating, which we're going to discuss later on the next slide. So yung previous monochromator natin na dispersing, it's based on refraction. So when you have a grating monochromator, this is based on diffraction. So you have a transmission grating, so where the globes or slits placed on a transparent material, same as earliest examples show in the diffraction discussion. Okay, so if you're going to look at this, the gratings that we have, try to look at my notes that I have here. So the way that you look at this, if you look at the order of the interference, so n here, okay, times the wavelength is equals to d times sine theta. So at different wavelength, it will have constructive interference at different points. And the way that you're going to do is you can select the desired wavelength by letting light at different points into the instrument. So if you do it like this one, I think we discussed this in our session, one of the last lecture that we have synchronously. So if you see the light there, okay, ito yung magiging product niya. So this is the 0 here. And then this is the one on this side. So this is transmission. Now the other one is reflection. And this is the one that is most commonly used. Okay. So here you have a group surface with reflective coating. So yung coating niya is either aluminum, gold, and platinum. And if you're going to look at this, the normal grating that you have there, so whenever you have light, okay, so at a certain wavelength, okay, this is equals to d sine of the incident light here plus sine of the reflected light. So the way that you do here, the d that you have there, that's the spacing of the slits. So that's the distance from one group to another group. Ito yun. Now, usually you have what? 300 to 2,000 groups per millimeter. So you can have both the constructive and destructive interference happening because light travels the different distances when reflected from each grating. And the angle at which constructive interference occurs is now given as this. Now, there are two types usually of monochromator. And I think pag binasa mo nyo yung angle, okay, it's there. So, yung tinatawag natin si Cerny-Turner grating. Okay? So, when we have this Cerny-Turner grating, it is comprised of a number of elements. Ano yung mga elements or components na meron tayo dito sa grating na to? So, meron kang entrance slit. Okay? Tapos, in that entrance slit, you will have lens or mirror. These are just what we call a system of lens or what we call mirror. So once you have this, the light source coming here in the entrance slit, so it will hit either lens or mirror. So what they do is they reflect some of these what we call light that passes through. And then it will hit this grating or prism. So based on the angle that you use there, it will generate, okay, the particular wavelength that you have. Ano sa tingin niyo yung pinaka main problem ng old instrument, nung manual pa siyang ginagawa? Whenever you have a system like this in the mirror, there's always question on the so-called misalignment. At least ngayon, automatic na lahat. But noon, they have to align everything manually. Okay? So yung collimating lens, ito yung nandito. And then, what happened? You have the focusing lens or what we call the mirror. So yan yung bago lumabas yung light source. At pag lumabas yung light source, ano na yun? Yun na yun, sinet ninyong wavelength sa monochromator. Now, there's another system of what we call monochromator. Yung tawag naman dito yung Bunsen prism. So look at the difference between the two. Anong makikita yung difference between the two? Anyone? Ano makikita niyo yung difference? Do you see this? Okay, so that's just the lens. But out of this, what happened? You see this one? May dalawang wavelength kang makikita. So the component is almost the same as what we call the Cerny Turner thing. But what do you think is the main difference between the two? Anyone? Cerny
Polychromatic itong Bunsen prism, sir.
monochromatic?
Poly po.
Polychromatic, okay. So if you're going to look between the two, okay, dalawa yung wavelength na nakukuha mo dito sa Bunsen burner or Bunsen burner tuloy, Bunsen prism na monochromator. Okay? And if you're going to look at here, prism, mostly prism, but you can also have what we call gratings in that thing. So if you're going to look at the Bunsen prism, okay, usually the first wavelength is higher than the second wavelength. So yung collimating lens mo, okay, so the collimating lens that you have, so this is your light source. Okay, so you have a collimating lens here, so it makes radiation parallel before hitting the dispersion element. So usually you disperse the incoming white radiation into parallel streams. Okay, and once you have a prism on which the incoming radiation is dispersed at both surfaces, and then you have another lens, this time you focus the collimated beam to rectangular points along the focal plane. And in the exit slit, which can be narrowed or enlarged depending on the resolution that you're going to look at. So, dito parang titirahin ng collimating lens, okay, daan tayo dito, daan tayo dito, daan tayo dito, and all of them will give you different wavelength and the focusing length until it will just release in the exit slit the wavelength that you're looking for. Sa tingin nyo, alin yung mas mahal? Alin ang mas mahal sa dalawa? Anyone? Yung Bunsen o yung si Cerny? So since po,
Bunsen po.
yung Bunsen yung what we call more expensive. In fact, mas mahal yung instrument mo with this one. Yung si Cerny yan yung pinaka ano. We could say standard nung Spectronic 20. Okay? And then we can also look at gratings versus prism. So we could look at them, differentiate them in terms of the type of dispersion. So the grating, you have a uniform dispersion, okay, at a particular wavelength versus a particular wavelength. Now, prism, on the other hand, they have the shorter wavelength has a better separation. Now, in terms of the size, grating is smaller than the prism. And in terms of stray light, I think grating has a lot of stray light. Okay. Now, I think one advantage of the grating is you have an unlimited wavelength range. It is applicable in wide wavelength compared to what we call the prism. You only use it at a wavelength that is less than 350 nanometers. Okay. So you can increase the size of either the prism of the grating to give you a better dispersion. And you can always relay what we call remove the straight light by using filters. Now glass would absorb what we call wavelength that is less than or equals to 350 nanometer. So usually prisms are made up of what? Glass. Okay. So another way that we can look at this one, yung we could say dispersion nila. The dispersion of prisms is what? Okay. The dispersion of prism is nonlinear compared doon sa grating, which has a linear dispersion. So yun yung, we could say, difference no dalawa. And then we can also look at the so-called slits in the monochromator. So you need to be careful. This need to be carefully made since the control of the range of the wavelengths emerging from, it controls the range of the wavelength coming from the monochromator. So usually yung leads mo is from 0.01 to 2 millimeter, and it is adjustable. Okay. So what the slits do is it's some sort of a band pass of the monochromator. So usually this is ito yung leads eh. Okay. So there's a range of wavelength that is transmitted, and usually at half height of the transmitted light band. So if you're going to look at the half light, ito yun dito. So the typical band pass would be 20 nanometer to 0.5 nanometer per UVBs. If you're going to decrease the slit size, you are also going to decrease the band pass, which is good. Okay. You have the less undesired wavelengths, but less intensity, and unfortunately, that is what we call TAD. So as much as possible, you want a smaller slit size. But usually it's already preset. Okay. So if you have two wavelengths, you can resolve it by the monochromator if they differ by 2 or more times the bandpass. So we could say the resolution of the wavelength is directly proportional to the slit size. Now, the next thing that we can do is the so-called filters. So in our monochromators, we can have these absorption filters. Ano sa tingin niyo yung filters na ginagamit natin araw-araw? Lalo na pag summer. Ha? Wala kayo nun, yung shades? That's a filter. What does it filter?
UV light, sir.
The UV light. Yeah, hindi nyo alam yun.
Yung polarized shade.
Yeah, the polar, yeah, the polar one or the ordinary one. Okay. So there are different types of what we call filter. One is the absorption filter. So this is the material that removes the undesired wavelength by absorbing them. So typically they're made up from colored glass or dye. The one that I usually use is orange in color because we want to remove especially the UV region that we don't see. Okay, and it can be damaging in your eye because it's high energy. So typically, typically made from colored glass or dye suspended in gelatin between glass plates. We have a fixed wavelength, much energy lost due to absorption. And it's usually cheap. So what it do, it wide range of the wavelength allowed through, and it combined filters with different wavelength range. So typical band pass, 30 to 250 nanometer. So if you have an absorption filter here, okay, so depending on what you have here, so the green and the orange. So this is what the shorter one. So if you don't want that one, you have what we call a filter that cut it off. So only the orange, okay, will be used. Or sometimes you can cut that off and you have what we call the green. So the filter will absorb the material, or we could say the light based on the wavelength. So effective bandwidth for two types of filters and the result of the combining what we call filter. Now you can also have the so-called interference filter. So what the interference filter do is you you apply the white light, and what it do is it just narrow the wavelength. So it's made up of thin layers of metal and dielectric materials like calcium fluoride. Okay, it's sandwiched between the glass plates. So the dielectric material is of uniform known thickness and the metal would act as a partial mirror. So usually ito yung pag-sandwich niya. So you have the dielectric material there, and then metal, and then glass. So you sandwich it. I think that's what you do usually, similar to IR. Yung hindi pinipellet, yung sinasandwich. Because some of the IR, you can pelletize it, you mix it with KBR. Pero KBR talaga yung material doon. But we also have the one that sandwich the thing. So what the interference filter do, okay, as light enters, some goes through, but some is what we call reflected. And the distance the light travels before it exits generates constructive and destructive interference on the other side of the filter. So the wavelength transmitted to the filter is equals to n, okay, which is the integer of the wavelength, equals to 2 times the thickness of dielectric times the refractive index. So the bandpass there can be 1 to 20 nanometers, so narrow, but the filter is fixed at a given value as much intensity is lost due to reflection. Now we go with the sample cell. So as I've told you, okay, you can have different what we call thing. I'm trying to do, ano bang pangalan ng company na yun? Every year, suki na ako dun eh. Tingnan ko nga yung email ko. Because every year, I always order some. Kasi dito, parang ano lang yung ano eh, yung sample cell. Pag nabasag, sige, palit lang. Star na. So, yun yung ano, star na cells. So usually, I'll try to show you. So, ito yung parang company. So, ito yung different ano, sample cell. Nakikita nyo?
Sir.
Kita nyo? Star na?
Apa.
Okay. So, kita nyo, hindi sila lahat 1 centimeter. Kita mo to. Kita mo yan. Tapos merong ano, usually ito mas mahal. Usually, what I bought is a fluorimeter cell. So, depending kung ano yung semi-micro or micro. So, usually, I think I use this one. The stopper one. So, that's what they had. Wala yung pressure nila. Usually, nakalagay yung pressure nila dyan eh. So, it tells you the wavelength, the length that you have. So, usually this is 10, that is millimeter, which is equals to 1 centimeter. So ito yung different ano, cubette. Baka sabihin nyo, ito lang yung alam kong cubette. Okay? Medyo, yung iba nga medyo manipis pa eh. So if we're going to look at the sample cell, first thing that you need to do is transparent. Sa IR, kahit hindi transparent, okay lang. Okay. So what you have is either quartz or fused silica, for those if you want to go lower than 350. Or if it's higher than 350, you have glass or plastic for the visible region. So best if you have a flat cell with matched samples and reference cell. So to make sure you have what you match them, you usually use in at least in our country, di ba? Isang cubette lang. So doon mo na lahat i-measure, right? Now, there are many automated instruments that have the flow-through cells with temperature control. You seldom have this thing. But that's all what we could say. Yung flow cell na meron dyan. So, papasok dito and then lalabas dito. They can do that. Okay, but I never have experience using that system. Especially if you're monitoring within time what's happened during the reaction. So they have that thing. So the other one that we have is the detectors. So our eyes is, we could say, the detector that we have. Okay. So the areas detector where the eye or the film. Now, if you use the device that usually detectors use devices that convert light into electrical signal. So for a good detector, you want to have high sensitivity, good signal to noise ratio, constant response over the wavelength or range of interest. The signal should be proportional to the light intensity. Okay, fast response, you don't want the response to be too long, and then little or no signals in the absence of light or dark current. Now, there are a lot of these detectors for UVBs. Okay. So maybe we can just roll on some of them. So one is the photovoltaic cell. So usually what we do is it's just part of the instrument. Okay. So the way that it is, light of sufficiently high energy passes through the thin transparent silver layer and hits selenium, causing electrons to be released, which move across barrier towards silver layer, electropositive, and collected at iron layer to neutralize the selenium layer. So the way that you have here, the current produced is proportional to the photons hitting the surface. The maximum response is at 550 nanometer. Advantage, cheap, rugged, no external power source, good for portable instrument.
Ay, sir, yung nakashare po ay yung star
Ay,
na pa rin po.
Star na pa rin, sorry.
Okay pa.
Okay. The problem with portable instrument, they're not very sensitive and sometimes fatigue. It shows some fatigue. So when it shows fatigue, the signals through time decreases. And it's difficult to amplify the signal small resistance that's caused by the Ohm's law. And then we have the vacuum phototube. Ito yung medyo luma. Okay. So it's just based on the so-called photoelectric effect. Okay. By Einstein. So you have here a photoemission material, cesium oxide. It ejects an electron when hit with a photon, the classic photoelectric effect. So the way that the current is proportional to the number of photons, okay, and smaller current than the photovoltaic cell, but can be amplified because of the larger resistance. So if you're going to look at this, what we call Phototube Advantage, sensitive, signal easily amplified. The disadvantage is some dark current that can occur. And this is due to the thermal emission and natural decay of potassium-40 in the glass tubing. So you're going to look at here, okay? The vacuum phototube is just sensitive to certain wavelength. You follow the thing that you have here. So depending on the material that you have. The one that is usually commonly used is this photomultiplier tube. So I don't see, do you see the thing here? Yung animation? Kita niyo animation dito sa right
Yes,
side?
sir.
Yeah. So
Kita
the way
po.
that you do here, so kapag nag-ano yung signal mo, ang ginagawa niya is minumultiply niya. Okay? So the light would hit the cathode and electrons are emitted, and an electron emitted is attracted to electrode 1, that's the diode 1, which is 90 volts more positive, causes several more electrons. Parang nagpo-photo-multiply yung signal mo. Okay? This is very sensitive to low intensity and it has a very fast response. The disadvantage of this is you need high voltage power supply and intense light damages. Ito yung sinira ko. I use a laser and the photomultiplier PMT was really fried. Intense light damages. So you have to make sure that your light is not too much. Kasi pag too much, ma-produce na current, pwedeng masira yung PMT. So this is one of the common. Okay? Pero ang pinaka-common ngayon ay yung PDA, yung photodiode. So the way that it uses semiconductor material where it conducts current only under certain condition. So the way that it happens is the light shining on the silicon diode provides the energy needed for the electrons to travel into the P region. And the flow of current is related to the intensity of light. Okay. So if you're going to look at the photodiode electrode tube, it's not very sensitive, but it's very useful in Vidicon tubes. And they usually use this for 1 and 2 dimensional detection. So ang advantage itong photodiode array, pwede kang mag-multi-wavelength. You can determine the absorbance at different wavelength. Okay? Kasi yung isang wavelength lang. Ito, pwedeng more than one. Okay? So the way that they do is to use this tube. It contains many silicon diodes insulated from each other. And the electron gun or light source sweeps the P region and charges the diode. So para yung TV. Okay? TV is just what? Yung old TV. A big cathode ray tube. So ito yung commonly na available sa mga UVBs. It allows you to determine a different wavelength kung ano yung absorbance nila. So you can have a single beam and a double beam. Okay, so both of them determine the absorbance. Okay, the light that goes in and the light that goes out. So both of them depends on the intensity of the source, the slit width and the wavelength of the monochromator, the reflectance of the cell, and the sensitivity of the detector. So if you have the classic spectronic 20, that's your single beam. So if you're going to look at this, the light is transmitted, it's measured with the solvent in the cell. So to get the blank, which is everything except the compound to be analyzed. So usually you adjust your spectrometer to read 0. Diba? Usually when we put the blank, meron yung auto 0. So ibig sabihin, the blank will read 0 absorbance or 100% transmittance. Okay? And once you have that, you can read yung meron kang sample mo. So any signal that comes there is from the sample. Is the blank always water? Dapat ba yung blank water?
Hindi po always, sir.
Okay. The blank should be everything except the sample. Okay. Now the best thing that they do is sometimes blank, sample, and then sample. But the best thing you do is blank and then sample, and then after that blank again, and then the next sample, because there might be a drip. Okay, this could be a change in the light source intensity, and the settings are usually wavelength dependent. So you're familiar with this one. Maybe right now it's instead of that line, you have a number. So the way that you have here, that's your sample, and this is where you adjust the wavelength, okay? And this is where you set, right? You put the blank and then you set it to 0. You still remember that? And then after you set it to 0, you remove the blank and then you put your sample. So if you're going to look at this one, so this is the light source, the lens, the entrance slit, objective slit. So this is where the monochromator is, okay? And then you have your cuvette here, and then your what we call detector. That's the Spectronic 20. So single beam spectrophotometer, the phototube that they have, sometimes it goes to 950 nanometer. Now the reference phototube electronically adjusts the changes in the source intensity, and the wavelength control turns the grating. So the 0 transmittance adjust sets the meter to 0% transmittance when the occluder blocks the light beam, and the 100% transmitted adjust moves to a B-shaped slot into or out of the light beam, so the meters reads 100 what we call percent transmittance. Advantage, chipipay siya, rugged. I think tatlo na yung tinapon namin Spectronic 20 since I moved to PACE. The disadvantage, you always have to adjust it to 0 absorbance at every angle. And you have to check periodically for the drift. So ang rule nga namin dito, there's always a cuvette for blank. So everything blank, sample, blank, sample, blank, sample. Okay? Now we don't have, no, I mean, the UVBs that we have has a double beam, but usually we only use one, what we call cuvette holder there. We just set both of them to 0, and then we set the sample here. Okay? So this is a Hitachi UVB. So you select a mirror or a beam chopper. So the mirror usually rotates at 60 counts per second. Okay? Reflecting the light alternatively to the reference and the sample cell. Now usually all lights go together, and then they combine and goes to a single photomultiplier. Okay? Now the advantage of this one, you can do scanning. Doon sa Spectronic 20, you cannot have like that. What you have is you just select one wavelength, tapos yun yung absorbance mo. But here you can do it like this. Okay? There's a little drip, only 1 PMT, and of course this is more expensive and a little bit complicated. So that's it. So I hope you maybe, if not learn, understand more about the absorption. So next meeting siguro yung application niya. Okay? So I'll try to what we call move on the different spectroscopic method that we have. So maybe next week we go on what we call atomic absorption. So question, 11:30 na pala. Meron na kayo ng reading materials na exam natin? Kasi hindi ko makita yung ano ko eh.
May sinend ako sa'yo, sir.
May sinend ka? Titingnan ko.
Opo.
Sa email ba yun? O sa chat?
Chat po, sir.
Talagang windang ako, to tell you frankly. Patapos na yung exam namin eh.